Welcome to this Click to Computer Science webinar, our virtual workshop. We're going to be talking about computational thinking and particularly decomposition, and working some more with some CS Unplugged activities and Scratch. So we're really glad to have you with us today. My name is Sandra Frerichs, and I'm part of the Click to Computer Science, Click to Science team. And I'm going to turn it over to Anne, who's going to introduce herself and get us started today.
Hello, my name is Ann O'Connor, and I am a project manager with the University of Nebraska-Lincoln. And my background is science education, both formal and informal. And I have also done some with engineering as well, teaching both adults and students. So now that we've done the quiz, we're going to get started with an introduction to computational thinking. Did you want to go through the agenda, Sandra, first, and then we'll get started with that?
I just wanted to make sure that people know this is our agenda. Yes, I was supposed to do that, wasn't I? We're going to move pretty quickly today because we've got a lot to cover, but we'll come back to this at the end. Our goal is that you are growing in your confidence in facilitating computer science experiences. I know several of you have been to the previous webinars, so we hope that you continue to gain more strategies and benefit from doing these hands-on computer science activities.
All right, so first we're going to start with an unplugged activity from code.org to practice. And unplugged activities are activities that are fun computer science experiences that reinforce important skills, but they don't require a computer. So they're particularly helpful if you don't have good internet capabilities in certain locations, or if you're just getting started with computer science. Some people find these a little less intimidating to get started with. And we're going to introduce this unplugged activity with a video called Computational Thinking.
The lesson on computational thinking is intended to teach you how to take a big, difficult problem and break it down into several simpler problems. The goal of this lesson is to write a set of instructions that someone can follow to draw one of the monsters included in this lesson plan. Students will break into groups to write instructions, and then they'll switch them with another group that will have to draw the monster. Groups will write instructions using the 4 steps of computational thinking: decomposition, pattern location, abstraction, and algorithms. First, groups will decompose the task, which means make a game plan. Then, they'll look for patterns between all the monsters in the catalog. When they come across differences between the monsters, they'll abstract out or remove those details. For instance, one monster in the catalog has Vegetas eyes, and another has Spritum eyes. But they both have eyes, so we can write a line that says, this monster has blank eyes. So students will be able to write a set of instructions called an algorithm that lists the monster's parts with blanks for what the style should be. This is the set of instructions they'll pass to other students to recreate their very own monster.
There was some vocabulary in this video that may be new to you, and she mentioned the 4 steps of computational thinking, and some people call these practices. And we're going to be using these terms today, so we wanted to make sure that we're all thinking about them in the same way. So I'll give you about 30 seconds to go ahead and just read through these definitions, and then I'll discuss them a little bit and how they're used in this activity. In the monster activity, Learners will decompose the problem as they identify the different parts of the task and make a game plan. And then they will look for patterns that are shared by the monsters in the catalog. And abstractions will help them focus on what parts of the pattern are true for all monsters, which would be the words that you put in rather than the spaces, like they all have eyes. And then what differs from one monster to the next, like the type of eyes that they have, which she discussed in the video. Then they should be ready to write a simple set of instructions or an algorithm that another group can follow to create the monster they've described. We separate out these practices to talk about them, but really they all happen together and build on one another to create computational thinking. So now we're going to share a video of youth actually doing the monster activity that you just saw the instructions for in the previous video. And as you watch this video, look for examples of youth using computational thinking practices, and what do these practices look like in action?
And the challenge is to write a set of instructions to make a monster that someone else could follow. They looked at a monster. First was to see the different portions of the monster and begin to look at the big challenge before starting the rest of the computational process. What are all the different parts you see amongst those monsters? Heads?
Hair.
And then they went on to that next step from decomposition, where they're breaking it apart, and they started looking at patterns.
They all have eyes.
Okay, so they all have eyes.
They all have ears, noses.
What we would like you to do is figure out a way to write an algorithm. So see number 4 up there? How can you put this together as a series of instructions that someone else could follow? And then, once they had all of those parts in that second part of the activity, they designed their own monsters. So they drew their monster, they wrote the instructions, and then they started partnering with each other and describing orally the instructions to build their monster.
Rigid mouth. Now can I draw yours?
What youth do in this activity is create a unique monster and write an algorithm or instructions for others to follow. The skills they're practicing are computational thinking, decomposition, and pattern matching. That makes the challenge easier to solve.
So what are you reading to me? What's it called?
Algorithm.
Nice, algorithm. Okay. And what's next? Which mouth? And did we get the same? Yeah, we did. Nice, thank you. I followed your algorithm. And in this activity, again, they applied all 4 parts of the computational thinking method.
So I have a couple of questions for you, and you are welcome to either type your answers in the chat, or you can unmute if you'd like to verbally tell me your answers. So the first question I have for you is, what did you notice in the video? And that can be absolutely anything, from the instruction to how the room was set up. All right, someone said the kids were engaged. I agree with that. I think he had pretty good engagement with the students. And even if he wasn't the one that was talking to them, I still noticed students working in the background. So they were interested in the activity. I think that's a good observation. I think the instructions were simple to follow as well. And he specifically was very careful about this, because these students are actually all English is a second language for them. They are all originally Spanish speakers. And so he was very careful about trying to make the instructions simple enough for them to follow, because some of them had very low English. So I think that was a good observation. It was fun. They worked together in small groups, are definitely some other things. Is there anything else that you noticed? And he did use vocabulary as well. Somebody pointed out that he was using the term algorithm. He did try to be very methodical and careful about how he used the vocabulary and when he used it. All right. So then the second question I have for you is, how did youth use the computational thinking practices in this video? What did you notice, or were they using them? All right, one thing is they were able to point out patterns, and they were looking at the similarities. Yes, and he had them do step-by-steps. He had them break down the monsters into the individual components. So that was part of breaking down the problem. So that was one of the practices we were talking about. Is there anything else that you noticed about the computational thinking practices he was using? And somebody said that he wrote down the ideas as they were brainstorming. I think that's a really important part of brainstorming. He wrote down everything they said. He didn't just pick and choose what was correct or what he wanted to write down. He was writing everything down. So that is a really good observation as well. So after answering those two questions, this video introduces this activity. Now we have a second video that we also want to show you, which shows you a little more about this activity and also continues to show how he was working with students. And as we watch this video, I'll have some questions for you at the end as well.
And you want to talk about active learning before we go into the video?
Yes, that's a good idea. Active learning is a learning activity in which the student participates or interacts with the learning process, as opposed to passively taking in the information. And so when you are given the opportunity to actively engage with information they're learning, students perform better. So as you watch the video, you can think about, how is active learning being done, or do you think active learning is being done? And then I'll ask you the other questions at the end. Thanks, Sandra.
What do we do when we take something big and we break it into its parts? What's that called? Decompose. So
An important strategy when embracing active STEM learning is to get youth to work through difficult assignments and allowing time to create on their own or with partners. Watch as Dagan facilitates active STEM learning in a hands-on, offline computer science activity. Notice how he explicitly supports youth in breaking the problem down into smaller steps, a key aspect of computational thinking.
what are all the little parts in those monsters? On that yellow page, can your team look at that? What are all the different parts you see amongst those monsters? Heads?
Hair.
I'm a decomposer. Breaking it into their little pieces. I love it.
Notice how Dagan breaks the process down so learners only have to manage one part at a time.
And what we would like you to do is figure out a way to write an algorithm. So see number 4 up there? How can you put this together as a series of instructions that someone else could follow? Is this your monster? So what would be your first step? Choose which head? Okay, so step 1 is choose a Franken head. Then what?
Dagan supports active learning by having youth test their own ideas with a partner. He is not the one who decides if their instructions are complete.
A lot of you have a monster drawn. That's awesome. What I'd like you to do is to make sure that you have instructions written and at least one other person has drawn your monster, just to see if your algorithm is correct.
Split them ears. Some split Yes. Monster's eyes. Vegeta's nose. And Vegeta's mouth.
At the end of the activity, Dagan tests out an algorithm or set of instructions written by one of the groups.
He has happy head, Then Zach closed his eyes.
Vegetas Mount. Oh no. That looks like a lot of detail. Let's see how I do. Okay, and did we get the same? Yeah, we did. Nice, thank you. I followed your algorithm.
So again, you're welcome to type in the chat, or you can unmute if you would like to answer verbally. So the first question that I have is, how does Dagan engage youth in active STEM learning? Okay, the hand motions for decompose, and he actually had, you didn't see it in the video, but he had hand motions for all 4 of the practices. And so whenever they were doing those practices, he would have them do the hand motions to help them remember that. That's a good example. Does anyone have any other examples of how he engaged them in active learning? Okay, he used ELL strategies, like having them repeat, that's correct. And breaking down the activities so the students could focus on one part at a time is also a good way to help students keep up and feel like they can do the activity rather than giving them too many instructions at once. So how did the questions help make an active learning experience? I think open-ended questions is definitely a way to help it be active, and it allows the students to really think in different ways. So there weren't necessarily right or wrong answers to every question he asked. Sometimes it was what they were thinking. So that's definitely a strategy. And he did use a lot of questions that was mentioned a couple of times. So he got the students thinking and making their own decisions. And Anne had mentioned earlier that they were allowed to use their own algorithms, and they got to design their own algorithms. So they got to determine if their algorithms were working and how to put those together. So there wasn't just one answer for it. So the last question is, how do you know if youth are engaged in active learning? And this is can be about assessment in formal education, but in informal education, you want to know that they're learning something. So how do you know if they're engaged in this active learning? Okay, they are participating is definitely one thing that I would look for. Reflection is definitely a piece of that as well. If you're having students reflect, facial expressions are important. And just as you look at a room, if students are engaged in active learning, you often will see them doing group work, or you see them talking to each other, moving around the room. So there are a lot of different ways to see if students or youth are engaged in active learning. It's just what types of strategies are being used in that setting. All right, thank you for participating in answering those questions. And now I'm going to turn it over to Sandra, and she is going to talk about our next activity.
Thanks, Anne. This is where you're going to need the first of those handouts, the Graphic Organizer, because we're going to be thinking more about active learning. And I typed it in the chat, but I want to say this too, so everybody hears it. Active learning, oftentimes we think about whether kids are able to move around, they have some voice and choice in the learning, and those are critical elements of active learning. Hands-on activities or small group work, as Anne described, are good indicators that active learning is happening. But it really comes down to whether they're actively engaging with the concepts, they're engaging with the information. And I want to mention that because what we're going to do next is we're going to think about how active learning can be integrated into the computational thinking practices. So in this handout, you have each of the 4 practices that we talked about earlier: decomposition, pattern matching, abstraction, and algorithm. We noticed how those worked in this activity, how they were able to break the problem down, look for the patterns and the features that the monsters had, and then take what they were observing and abstract that into a algorithm or a set of instructions that would work for all of the monsters. That's kind of how they come together in this activity. And what I want to brainstorm here using the graphic organizer is what are things you can do that promote active learning, kids really engaging with those practices for each of the 4 practices. You can think about this specific activity if you want to, or you can think about a computer science activity in general, or maybe a specific activity you're going to be doing coming up. And we're going to break into breakout rooms to do that. We'll have 2 different breakout rooms so that you have a small group to kind of work through the worksheet together. And then we'll come back together in about 10 minutes to talk about what you noticed and what you found in that. If you finish before we close out the breakout rooms, just go ahead and exit your breakout room and come back to the main room, and one of us will be here, so we'll know that you're ready to move on to the next step. So we want to come back together about 37 minutes after the hour. And Anne, you want to go ahead and put them into the breakout rooms? Oh, wait, before we go, does anybody have any questions? I should ask that before we drop you into breakout rooms. The 2 questions that were on the slide are on the chat here, so you'll be able to see them. Oh my goodness, we lost 3 people immediately as soon as I said the B word. Okay, well, still, you know, with a group this size, maybe we'll just all stay together rather than in breakout rooms. So I invite you to turn you want to go to breakout rooms? Feedback here. 2 breakout rooms or all together? Okay, go ahead and open the breakout rooms. I can't believe they ditched on us that fast. Or I can do it.
There.
Oh, perfect. Welcome back. So I kind of wanted to hear what you had. I dropped into each of the breakout rooms, but I didn't want to interrupt you as you were having your conversation. So let's just go through each of the sections on the handout, and I'm anxious to hear what you thought about. I think decomposition might be a little easier than some of the others to think about how they were using, how you make that active. What ideas did you have?
Well, I guess I'll talk for our group. For decomposition, we were talking about the hand motions and props. And we were thinking a lot. Well, one example would be like that Chase mentioned was building makey items, kind of how you break it down into steps to build something. We talked about having them explore on their own. And then breaking into groups for more cooperative learning or small groups.
Anne mentioned using lots of questions. There were lots of questions and back and forth in that part. How about pattern matching? Maybe somebody from room 1, can you share what you guys talked about pattern matching, since room 2 jumped up first? Thanks for doing that, Lisa. I think in this activity, specifically, the pattern matching section was pretty short. But were there anything that you noticed? Visual clues, the brainstorming on they brainstormed in the pattern matching on the whiteboard, and then when they were doing decomposition, they brainstormed the features and he left it up on the whiteboard. He accepted all the answers. And then when they got to pattern matching, he was circling the ones that they identified that were part of the pattern. I think you're right, Jonathan, that was really important, because then when they got to the part where they were writing their algorithms, those features that were circled were the ones they needed to include in their algorithm, so that he was giving them that clue that they could come back. And again, it was well, we'll talk about this a little bit more, but the students were making the decisions. He wasn't telling them which of the features were correct that they needed to include in their algorithm. He was just circling them as they were brainstorming. And that's an important part of the active learning, the deciding what answer was right, evaluating the responses. He really put that on the students rather than giving them a lot of feedback on whether they were on track or not. The next part of the activity was abstraction, where they went from that list of features to thinking about how to turn it into instructions that would work across any of the monsters. I found this one the most difficult to think about in terms of active learning. I think partially because it didn't take them very long. They went through that pretty quickly. But was there anything that anybody else noticed in the video about the section where they're going from having features to then thinking about how do you abstract that into a set of instructions?
We just mentioned that he gave them a lot of vocabulary too.
Yeah. And this one may have been hard to catch because we know that there's several videos about this particular activity. So I have seen a little bit more of it, but when he was introducing the vocabulary, he had hand signals for each of them. Like they use, I think, this one for decomposition. I don't remember what the hand symbol was for abstraction, but for each of them, as they were going through that segment, he was reinforcing the vocabulary and using that physical, the way they embodied the vocabulary with the hand signals to reinforce that for them and to make it active. And in this case, even just the fact that they were able to move is also an important part of active learning. The last segment was algorithm, where they actually came up with a set of instructions and they tested it with somebody else. And what was the active learning components there?
They were like, writing out the steps and, testing it out, having someone else try to draw their monster, at least one person.
Mm-hmm.
And so it allows you to kind of like revisit some of those steps and, see if it's nice and clear. And then the instructor, drew one of the monsters and they matched it up together. He's like, I followed your algorithm and it works. And he, got, verbal confirmation from the kid if it was, if it was right or not. So like still keeping them pretty engaged.
Yeah. I like that idea that it was the students who decided whether the algorithm was right. And that's one of the things that I like about a lot of computer science activities. I do a lot with Lego robotics and having the kids build and program Lego robots or any of the robots you can use now in the classroom. As a person facilitating the activity, sometimes I can't tell them whether their program is working or not, but whether they've got the code right is determined by whether the robot does what they want it to do. And I think that's a really important component of active learning, that there's not somebody else, a teacher, telling them what the right answer is. It's really something that they're discovering on their own. Either the robot, you can think about the robots telling them, or their friend is telling them whether it's the right answer, but it's not something that's determined by an authority. It's the right answer if it works, if it accomplishes what they want it to accomplish. And that's not always the case in all areas of the curriculum, but it is something that I really like about doing computer science in particular, that you can do that. And it's one of the reasons that it really lends itself to active learning. We don't think about sitting in front of a computer and coding for a robot as being a real active learning experience, because there is sometimes a lot of sitting, but there's also a lot of engaging with it and wrestling through those ideas on their own. The person leading the activity may not be able to tell them how to do it. They kind of figure it out as they're going. And that's really empowering for young people that can happen. So we started with this unplugged activity as a way to look through the computational thinking practices. In this particular workshop, we really wanted to focus on decomposition, or breaking the problem down. And we're going to do that next by looking at a scratch activity. And Anne, I'll let you take it from here.
All right. So the next activity we're featuring comes from a curriculum developed by the Harvard Graduate School of Education, and it's called Creative Computing. And this is free on the web, and we'll drop the link in the chat for you if you want to look at that later. Creative Computing uses Scratch to teach a variety of computer science concepts. And Scratch is a visual programming language designed by MIT. The curriculum has 6 units that you can go through sequentially, but today we're going to jump into a unit 1 to an activity called Debug It. And this is on page 40 of the curriculum. And these will be the other 2 handouts that Sandra sent you ahead of time. And so first of all, who can explain what debugging means? And you can, again, either type it or just unmute and tell me what you think it means. All right. Lisa is correct. It's looking at code and figuring out where there is a broken part. So it's figuring out what's wrong in your computer program that makes it not work. And this is an important skill to learn in computer science because everyone has to debug their programs. And the practices we've been using today are helpful in debugging. So think about decomposition, patterns, or abstractions that can help you figure out what the problem is. So Sandra is going to drop a link in the chat that you can click on, which takes you exactly to where we're going. And there are 5 projects in this studio. Each one has code that is not working quite right. So you will see what the code should be doing in the description here. And Sandra is going to demonstrate this for us. And if you have 2 screens, it's really helpful because then you can just be doing this on one screen while you have us on the other one. The electronic version of the worksheet is really helpful because you can just go and click on those links rather than having to go back. So this should be the screen that the link takes you to, and you can see there's Debug It 1.1. And then you open the program to fix or debug your code. So we'll do the first one together, but if you're familiar with Scratch, which some of you said you are, you're welcome to move through the activity at your own pace, and you can explore the creative computing curriculum. And we'll come back together about 2:10. If you want to just get started, you're welcome to mute me and you can go start exploring this. For those of you that maybe haven't used Scratch before, you just have heard about it, we'll go ahead and take you through this first activity together so you can figure out exactly what you're doing. So first, you want to read through the description so you know what is supposed to happen. So what's supposed to happen with this, Sandra?
It says both Gobo and Scratch Cat should start dancing. I assume Gobo is the yellow thing. I'm not that familiar with Scratch. I do recognize the cat. So I'm going to click on the green flag to see what happens.
Yeah, so then you click on the green program to run it. And then when you have run the program, then you can click on the red button to stop. And the stop sign ends the program. And then you can click on the See Inside button at the top right-hand side of the screen and look at the code that's making your sprite move. So as you look at the code for Scratch, which is the cat, you know that's running correctly, because if you looked at what you were supposed to be doing, Scratch was supposed to be moving and he was, so you know that code's correct. The problem is that Gobo is not moving. So you know that code is incorrect.
I want to point out here, because I didn't know this at first. Over here in the corner, lower right, there's the 2 different characters. So if I click on Scratch, I can see this code, and that's what is coded for Scratch. And I see Scratch up in the corner here. And when I click on Gobo, it goes to the other code.
Correct. And so the first question I always have when I'm looking at visual programming languages like this is, what do you see? And so the first thing that's helpful is just, what are you noticing? So are there different color blocks? Are there different color for words? Are there different shaped boxes? And how are they fitting together? And so that's the first thing that I look at if you're looking at a visual code. And so after you've kind of looked at that, and you can see over on the left-hand side of your screen, it gives you kind of an idea of what things are supposed to be doing. So if you have blue blocks, those are motion blocks. So they're supposed to be making your sprite move if you have it coded correctly, where you can go through, there's all the different colors, purple, magenta, yellow, everyone does something different. So if you know that you want your sprite to move, you don't want to be using magenta because that's not going to help them move. So when you understand the basics of the code and you've looked through the sprite code, then click on the Gobo sprite button at the bottom of the screen to look at the code for this sprite, which is what Sandra did just a minute ago, and try and figure out what is wrong with the code that is causing Gobo to work incorrectly. And if you know that the sprite Scratch works correctly, you use that code and you can look at that and try and figure out what are the differences between that code and the Gobo code and see if you can figure out what's not right. So I'll let you look at that. And if you have any ideas, you're welcome to type them in the chat or unmute, and then we can start seeing if we can figure out what's actually going wrong with this. And you're welcome to make your changes as well. Just try something with your code and see if it works. And then you can share it as well. So when clicked is missing, Lisa noticed.
I noticed that too. Did you catch where to find that? Because it's not in the motion commands. Did anybody catch where that would be?
Okay, under events is correct, I think.
Yep.
So there's your code for that.
And then it put this loop down at the bottom, which I want to make sure. So shall we see if it works? Now they're both dancing. We could go and make it really fancy and make them dance better, but this is the point that we want the kids to get to, and to be able to do that on their own.
Exactly. So we will let you now go through as many of the rest of them as you have time for. And let's come back at 2:10 and we'll go ahead about 2:10, maybe 2:08, 2:10, somewhere in there. We'll come back. And if you get through all of the other 4 debugging studios, you can go ahead and look at the creative computing curriculum, or you're welcome to go in and click on more links in the creative computing, and you can just keep doing this. They have other debugging lessons that they get more complicated as they go down the curriculum. So if you want to work on that, if you have any questions, please feel free to type them in the chat, or you can just unmute and ask Sandra or myself, and we will help you out with it. If there are no questions, you can get started.
We do want to give you a little bit of time to play with this on your own, but if you're done and you want to move on, feel free to let us know that too.
Yes. And if you are curious, there are Scratch tutorials located in the blue navigation bar at the top. So you can click on that if you're getting stuck. Debugging. So was it easy for you? Figured it out really quick? Or was it a little more frustrating? And you can either type or unmute. Okay. So we have one person that figured it out pretty quick, and another person that it was a little overwhelming. And you do gain confidence as you get code that actually works. You'll find students have their aha moments and they get really excited about it. And that is what sometimes hooks kids that really love coding into doing more coding, because they have that success when they've debugged their first program and they figured it out. So what made, for those of you that were maybe a little frustrated, what made you feel frustrated and how did you manage that? And I noticed several of you are already saying that you kept working at it and you figured it out. So that's one way to manage it. Did anybody else have any other ways that they managed it? Looking at comments can help you. You can see other people were frustrated about it at various programs. Some of the comments gave you answers, so you could just look at the comments and figure it out. And so how did you feel when you figured out what was wrong with the code? So hopefully all of you had at least one success. For those of you that figured it out quickly, obviously had some. So how did you feel about that?
One of the things I'm noticing is this is a group that hasn't been very chatty, but people are more likely to tell us that they figured it out, that they solved the problem. And I think that is how kids feel too, that it feels good to solve it on your own.
I think weight off your shoulder is a really interesting comment. Did you want to say any more about that, Chase?
Yeah, sure. That was answering the how did you feel when you figured out what was wrong with the code? And because you could spend, you know, it might be you find it in like a second, or you might spend 10 minutes or, you know, several hours trying to find, you know, one mistake or multiple. And then once you figure it out, then it's like, now I can breathe, or, you know, it's a sigh of relief.
Yeah, I think that's exactly the way your students are going to feel as well. And it can feel like a weight if you give them a whole bunch of code and then you're asking them to figure it out. It can look like a really big problem. So I think that is a really good observation. So how did you use your understanding of decomposition, patterns, abstraction, or algorithms as you were debugging, or did you not use that at all? And you just went to tutorials and you thought you figured it out that way, or read comments and got answers from that?
Yes, I kind of went through all four, looking at some of them, just like breaking it down into like, you know, are there two characters versus one, or you know, what's, you know, actually involved, and like breaking down the question itself. So they're supposed to go, you know, walk 10 steps, then looking at the code to see if, you know, are they walking 10 steps, patterns. So like with the two dancers, you know, looking at the code of the dancer that does work and looking at the code of the dancer that doesn't work, and, you know, seeing the difference. That was one, you know, one of the easier ways to kind of figure it out. And then the abstraction and algorithm, like just looking at, all right, well, I don't need all of these, you know, buttons. I just need to focus on, you know, what's going to, you know, complete the steps for any of these codes. So yeah, it helped, you know, to just break it down, especially when, you know, once the code gets a little bit bigger and you have more characters or, you know, backgrounds to deal with.
I think that is a good explanation of this. And I think of these practices as a thought process for solving problems in computer science is the way I personally think about it. And so it is tools to help students or yourself to have some ideas of how to solve these problems. And so I think that that was a good observation. And it is important to help students manage their frustration and stay focused on a growth mindset that they can find a solution that works, and then support them as they are innovative and try new ideas, even if their ideas don't work right away. And computational thinking is one way to help them do that in computer science. So as we explore computational thinking practices and specifically decomposition, helping students break a problem down into more manageable steps is one way to help them manage their frustration when things are not working right. So how did understanding computational thinking help you debug, or did it help you debug?
Now that I look at it, it's kind of the same problem or the same question we just talked through.
Yep, I was kind of thinking the same thing.
One thing I was going to add was just like going through those steps, maybe think about, you know, like, oh, those are kind of the same steps I use to solve like other problems in life, whether, you know, I'm walking somebody through a math problem, or, you know, so like, you know, breaking down the math problem, especially like word problems, because those can give kids a lot of trouble. And so like breaking down that part, and patterns, or like, you know, vocab. So like, did you see a minus? Did you see a times? You know, like what words did you see in those sentences? And so, yeah, just, working through those steps and like how it applies to like other areas of life. So it's like something you can like remind the kids of, that you already do these steps.
And I think that segues really nicely into the last question. And I was gonna say, I noticed a couple of different people said patterns, using patterns as something. And so I think some of us have different strengths in using these particular practices, or we're more comfortable using certain practices. And obviously different practices may apply in different circumstances. If you're looking at something with a lot of patterns in it and very little abstraction that you can actually use, then maybe you're going to work with more patterns, and abstraction isn't quite as useful in that particular circumstance. But we want youth to understand that computational thinking is a problem-solving process, just exactly what Chase was saying, and they can use it to solve problems in day-to-day life and not just in computer science, because it really is a way of problem solving. And there's an engineering design process in engineering that is also a way of solving problems, but it's different than the computer science a little bit. And so how would learning how to debug a program help the youth that you work with in real life situations? So now thinking about how to apply this in their everyday lives, how would you do that just with what you've learned today in debugging a program and using these practices? Maybe another way of thinking about it is what areas that maybe you either teach in or you work in. I know some of you are from libraries. What are areas that you could think of where you could use computational thinking that's not computer science? So I'll give you one example. I really enjoy baking, and following recipes recipes are an algorithm. So that is an application for a student that really enjoys cooking. Anytime they're following a recipe, they're following an algorithm. So that's one example. So do you have any examples of other areas that you could use these practices to explain how they're using computational thinking already?
Yeah, I would say just throwing more examples like that. Like, I had a kid yesterday who didn't know how to tie his shoes, and a friend came over and tied the shoes for him. And that's one of the ways, which way do you tie your shoes? And like, I use this method, I use that method. And like, just remind them, like, well, when you learn like this, these are the steps that you went through to figure out how to tie your shoes. And some other ones.
That is a nice example for young students. And sewing, Lisa said, that is a great example, because there are algorithms in sewing, there's patterns in sewing. Because I really like sewing, especially you're thinking about quilts, you can get into patterns and abstractions, and you can get into decomposition with how you're going to design your quilt, even if you're looking at several different patterns and you're needing to eliminate and simplify them. And so that is a good example of another area that you could apply these practices in. So I think that you're thinking about this in the right way, and always applying something to real life problems, to real world problems for kids, helps them connect to the information you're teaching. So I'm going to pass it back to Sandra, and she will wrap us up.
Forgot to unmute. Thanks, Anne. So these are the goals that we had when we set out today, and I really appreciate the fact that you stuck with us to get through this hands-on time, because sometimes it's really hard to take time to actually do some of these activities and to get into there and play around a little bit with Scratch. So I'm really glad that you took time to do that, and I hope you're leaving today with a better understanding of the computational thinking practices and how you can integrate them with active learning. And then also this conversation we just kind of wrapped up with about how this is an advantage. This is something you can equip your kids with to help them be more successful in life, to think through problems and approach them in a strategic way. The activities that we focus on today, computational thinking with monsters, is from code.org. And the Debug It activity is from the creative computing curriculum. And in my follow-up email about this workshop, I'll send you links to both those so that you can find those activities and use those in your program if it's a good fit. But getting those active learning parts in there isn't necessarily something that's covered by the curriculum. You can go through all the steps in the curriculum and really not give students time to wrestle with the ideas on their own, to have ownership of those ideas, to be the active learners. So that's really kind of where the art of teaching comes in, that it's more than just having the right curriculum. It's having those strategies in how you present it so that you can make it a great learning experience for your students. The resources that we use to put together the workshop are from Click to Computer Science. So we invite you to visit the website there, and there's lots of resources that you can use as you're leading activities with kids, and also as you're leading professional development, trying to build your own skills or trying to develop skills for the people that you work with.